This is Galactic bringing you another presentation in cosmic geometry. If you're not familiar with that term, don't be alarmed. Cosmos merely means the universe, which is rather a simple concept. At face value, it's a single thing. We're going to be talking about that today. What you see over here is a sphere with the parts that we are all taught in school. It has a center, that's the most significant aspect. It also has a radius, and then there's the great circle. On the Earth's surface, the great circle that we consider most often is the equator. And the equator is the most important great circle on a sphere because it indicates rotation. And all spheres in the universe rotate, all the way down to the electron, and we're working on the proton. We have a major discovery at hand. Galactic has discovered a new aspect to the proton, which goes beyond what Gelman discovered through mathematics, although it was never interpreted correctly. Galactic has interpreted the quark system correctly. It is a mathematical interpretation of the proton. One of the reasons that Gelman came up with his three-quark system was an attempt to explain both the proton and the neutron based on what is known about each one of these particles. It's actually one particle that was not discovered by Galactic, but we're bringing out that fact. The neutron is simply the proton in a different state. And this has been proved by physics because they transform into each other. So what we're going to do today is to canvass all the discoveries made here at Galactic over the past 3 years. Just to put it into perspective, it's about time this was done. I have been massively overworked in a most beneficial way. I'm not complaining at all. It's not overwork, it's sufficient work. Because the geometry that was discovered here just 2.5 years ago is spherical geometry, which turns out to be remarkably explanatory, and that's what we're going to be covering. The way we're going to cover that in this particular video, which is intended to be in a sequence, because there's a lot to cover. We're going to go all the way from the quantum to the infinite universe and explain each part. This is the duty, the job of science to do this so that human beings, not trained mathematicians, but just ordinary human beings, can understand their environment. So we do take that quite seriously here. That is the highest goal of science, and it is the only known goal, although it comes down to a personal aspect because it has to affect at least one human. Science is meant to help humans. We know that. Technology demonstrates that rational logic is meant to help humans. Now, currently, it is helping humans, as we all know. Technology is miraculous, but it has a serious, mesmerizing quality. Because when you have technology, of course you have governmental control. And we simply cannot have that. Governments ruin everything they touch. So we can't go by technology, strictly speaking. However, it is an index of our success. Okay, so that's enough of that. What we want to do now is show where we're going today. This is a very brief outline of our two-part series. I'm going to try to cover all of this in one lecture before we get into each part. This is somewhat fluid from my perspective, and I apologize for that. You should have a very clear layout of what's ahead. This is as clear as I can make it. You can see that there are 4 sections, beginning with the time section, time, universe, quantum, and atom, and then the second section marked part 2, geometry, line, orthogonality, and the Boschkovich force curve. Now, that's a lot. However, all of this is now integrated. The story of science is a story of integration. When you have knowledge, you have to integrate it into understanding. Of course, that makes perfect sense. I don't need to elaborate on that, although it's a fascinating topic. And I have elaborated on it in the past 660 lectures. I have covered that, but I never expect anyone to go back and sift through my unorganized videos. This has been a whirlwind. For over 2 years now, Anagalactic has been pursuing a geometric course of study in physics, and it has led in every direction with remarkable success. The latest course this week, Anagalactic discovered the structure of the nucleus of the atom, and that was unknown. It's still unknown technically. I know it, but that's not science. That's just one man trying to add to science. That is what I'm trying to do. I did not foresee this 3 years ago. I simply wanted to expose a new geometry, which is simply the geometry that physics knows it needs now. Well, physics doesn't really need anything. It's off on its own in technology. Well, where is physics for humans? Well, it's gone into Lulu land. It's psychotic, and everyone knows it. Technology now has led to a popular conception of science really based in technology, which is utterly psychotic. In other words, divorced from reality. Absolutely divorced from reality. Now, this is a tremendous attention getter. People are just so baffled, so confused, but curious, and that's blueprinted into us to be curious, to use our rational minds, to figure out reality. That is exactly the goal of science, is to rationally analyze reality for a goal that's hard to describe because it goes to consciousness. That is the meaning of existence. Now, of course, we all want to know that, but that is a personal thing, for obvious reasons. What science tries to do is use rational logic to interpret the universe. All right, I think that makes sense. We'll come back to this, but for now, I just want to outline the 8 items that we have in 2 sections. Let me show that one more time. We're going to start with time. Now, time is a major topic today, of course, and it really has been ever since Albert Einstein. You'll see that each one of these 4 items has an arrow because duality is an important aspect of geometry. And this is geometry in its most abstract sense, how we perceive the universe and reconstruct it in our minds. It does need to be reconstructed. Now, the way we experience reality is through a continuum which we call time, so that it's a moving balance point, you could call it. Now, time-space is well known now by the work of Albert Einstein. Time-space and space-time are interchangeable terms, although they actually have a mathematical distinction. Space-time is a construction of mathematics. What is the importance of space-time? Do you know? It wasn't perceived at first what the importance of space-time was, what Albert Einstein constructed. It's a 4-line system, as you know, 3 of which are given since Euclid, the 3D construction of space. Well, it turns out that that's incorrect. We really all have known, really since the beginning, that the universe is not linear. Now, there's a footnote, because distances can only be linear. And of course, that's what we use mathematics and geometry for in the Euclidean system, is to get distances between things, either on Earth or in space. So, that's pretty obvious. That's the nature of linear geometry. Now, that was extended by the Greeks to a 2-line system using orthogonality. Now, you'll notice that orthogonality is listed here, down here, the second to the last item. That ortho, I'm just going to write it out, orthogonality, right? And so we can, that's what we have to discuss today, superficially, because each one of these topics, of course, is quite deep. But we're going to begin and end on time. Now, if you want a more extensive introduction, my prior lecture, which was yesterday, very brief, but it was basically devoted to developing this outline, which I developed yesterday and today, so this is brand new. But it's covering all the stuff that I've done over the past 2 years in extremely abbreviated form, so you have a full picture of the synthetic approach that I take. Geometry by nature is synthetic. Now, what is meant by synthetic? It's really meant to be, in my usage of the word, the opposite of analytic. Analytic, you take things apart. And that's important. You need to take things apart in order to understand how the parts relate to each other. But it's the relationships that are most important, and that's called dynamics. When you're talking about the interaction between the parts specifically, it's mechanics. And mechanics and dynamics, I devoted an entire presentation to the distinction between mechanics and dynamics. It takes a while, even using Wikipedia and other tools, to get the correct relationship between how these two words are used. They're used virtually interchangeably, but they do have a distinction, but they're always used together. When you say mechanics, you're also talking about dynamics, and vice versa. So that's another duality. You'll see that all of these are dualities, not necessarily strictly speaking on the same order of duality. There are different kinds of dualities, and you may be acquainted with a very famous one. The first one that jumps to my mind is electromagnetism. There's magnetoforce, which is a force, and electroforce, which is very well known as a force. All right, so that's our outline here, and now I want to show you something. We have 8 parts to cover in 2 sections, so we're going to deal with the first 4 items, and here's what we have for that: space and time. So that is going to be our first topic. Now I want to show you everything at once, so you know where we're going. It's important to maintain continuity in a presentation of this nature, which is synoptic. It is to cover a broad span in a short amount of time. That's quite an art, and I'm still trying to master it. I hope I do well. Thank you for tuning in. That is our first item. The next item will be the universe and infinity, and we have something for that. That looks like the universe with a big infinity sign. We'll be covering that. This is the third item down, the quantum. Now, why do I have superposition related to the quantum? That's not really a duality, but it's the most important aspect of the quantum. In order to understand the quantum, you must understand superposition, and I'm not necessarily the one declaring that. That's Paul Dirac. Okay, Paul Dirac, in 1930, issued a book which is considered to be one of the most amazing books ever written by a physicist. Paul Dirac was a unique man in the way he presented science, the way he approached science. There are a couple of excellent books about Paul Dirac. So, the fourth item to end our first semester is the atom. All right, now we're going to switch to part 2. In the second part, we're going to talk about geometry. The reason I have it in bold is that's my approach to physics, is a geometrical approach. That's out of favor now due to the nature of technology. It no longer relies on geometry because it's considered to have been solved with spaceTime, which is a 4D hyperbolic system, technically pseudo-hyperbolic, but we'll get there. Now, geometry, to finish this, is related to mathematics. And we are all taught this in school side by side, but I will show you the more specific relationship between geometry and mathematics. It has more or less been inverted, so you could actually change this line to read geometry is derived from mathematics. Now that is incorrect, although they're so closely related that you could even say that they're equivalent. That's not quite true, but it's very close to being exactly true. The next item down in our second semester is the line, which you see I have pointing to continuity. Now, what do I mean by that? Continuity is not an aspect of the line. It is an aspect of the curve. The curve, any curve, has an aspect of continuity, but the straight line does not. The straight line has no aspect of continuity. Can you guess? Is it kind of a spot quiz just to wake up your mind here, see if you can think of it. If the line, as I say, does not possess the aspect of curvature, and therefore it does not have the aspect we call continuity, assuming that that's true, what then can you say about the line that takes the place of continuity? It's called quantization. We'll come back to that, don't worry. The third class or section or presentation or topic in our second semester is orthogonality. Now, orthogonality has always been considered to be the foundation of geometry, as you know. The reason is quite simple, is that if you have a line like this, but you want to have a plane, the line does not make a plane, but if you have another line, you can have a planar coordinate system. That's called 2D. If you add the third line to make 3D, to add depth, you have the capacity for really what you're doing is you're creating a coordinate system for volume space. We'll come back to that. All of this is synoptic and very hasty at this moment. Now, the next item down, which I've abbreviated BFC, is the Bošković force curve. Now, below that you'll see that I have two indented topics for the Bošković force curve that both have to do with orthogonality. This symbol here, of course, is the symbol for the perpendicular relationship. Perpendicular and orthogonal are synonymous. This word you may have heard of. What is asymptosis? In short, just so you have an idea, a working definition so this doesn't just hang in the air, what is being referred to, asymptosis is just an abstraction, to talk about the relationship between two completely different lines, one of which is straight and the other is curved. It's the relationship between a straight line and a curved line on a very specific mathematical definition. And the asymptotic relationship between a curved line and a straight line basically is a diagram of Zeno's paradox. And I'll go into that when we get to this part, which ends our 8-part sequence. This shows a rather suggestive little function. This is just a shorthand for the relationship between two infinities. Infinity has a couple of different meanings, depending on context. Infinity itself is a way to refer to something that is imaginary, and yet we know that it's there. If it's there and it's imaginary, it's a problem. So this is a way to get at infinity so that it's no longer a problem. And that is one of the most important discoveries made here at Anagalactic, which can be summed up as the rationalization of infinity. All right, why do I put time first? Because it's so difficult to define. The nature of this presentation will be to go through this sequence, but with a directed aim. That is the nature of science, is that you're looking for a solution to a yes-no question.
Binary logic.
In order to define time, you have to define it according to the scientific method. That's not going to be an easy task for the simple reason that nobody yet has been able to define time. So for me to define time will require going through these 8 steps. So this is an approach to time. And when we reach the end, our 8th topic, the Bošković force curve, and we get to the second item, The perpendicularity of two infinities, quite a remarkable thing even to be able to say. Physics does not know what time is. Now, that's where we begin. What do we know about time? Albert Einstein gave us really the immortal key. He didn't fully get it, but he made such an enormous leap. It's equivalent to, is it Buzz Aldrin who stood on the moon? But Albert took a mighty leap, because until Albert came along, using Minkowskian geometry, nobody had any idea what time was. And in the natural philosophy department, which used to be the name for science 2 centuries ago and more, there was no word science. The word science was invented in the 19th century. Before that, it was called natural philosophy. For fairly obvious reasons, lacking the proper technology, nobody could find particles and nobody could see the universe. It's very simple. So what is time? What time had been, for instance, to Newton, was a continuity, a continuous abstraction. And that's the most anybody could say. Nobody knew anything else about time. Well, what Albert discovered, a bona fide discovery, because this works. What did he discover? Well, what he was trying to figure out was essentially the same thing that Poincaré was trying to figure out, which was a way to synchronize clocks, believe it or not, for the sake of train scheduling. And they both were, in their own way, vitally concerned with this question. Poincaré was more hands-on in the sense of dealing with the train system, which was on the rise, of tremendous importance in Europe, and of course then quite quickly America. Trains really changed the landscape. Well, the problem then arose, really for the first time in human history, of how to coordinate local time. But you see, local time is different everywhere on the surface of the Earth. Obviously, it's a 24-hour ring. And so the time on one side of the Earth is 12 hours off from the time on the other side of the Earth. So how do you coordinate local clocks? Well, Albert worked on that problem, so did Poincaré. Now, what Albert figured out, and Poincaré was well on the heels of Einstein. They were both magnificent mathematicians working on a serious industrial problem. Now, for Albert, it was much more abstract. It took him quite a while to work out general relativity, which is the formula for gravitational space. All right. What is relativity? The best way to describe the power, the actual applicational power of relativity, is to consider spaceflight. If you consider spaceflight, for instance, sending a probe to Saturn, such as the Cassini vehicle, a tremendous photographic platform which got all the way to Saturn, there is a specific problem that must be addressed. In order to have interplanetary space travel, you have to be able to guide your remote vehicle from Earth. If you don't compute the time lag, you won't be able to control the craft. So space-time mathematics compensates for that by having a specific geometry, quite intricate, it uses hypercalculus, but definitely going to Mars and beyond. The difference between special relativity and general relativity, if you have a satellite system, as we do now, a GPS system, these are mini satellites. 24 is considered to be about the right number. And there's more than one GPS system. The Russians have one, and so do the Chinese. But the American GPS system is, of course, considered to be the standard. It was first. It was well done. But all of the satellites, that is, all the computers involved, both on the satellites and on the ground, have to be coordinated the same way that Poincaré and Einstein tried to coordinate train schedules for different localities, because the time frame is different. It's called a frame of reference. Well, you have 2 frames of reference if you're trying to get GPS, and in fact, one of the frames of reference is several satellites. You need at least 3 to get a triangulation. So it's quite complicated, and each one of those vehicles, the satellites, has a velocity. Now, because they're moving quite rapidly, there is a special relativity conversion. Because it's moving, there's a relativistic conversion, because it's a relative difference in velocity. So that has to be computed. It's on the order of nanoseconds, but without it, the system won't work. It'll drift, which makes it worse than useless, because then you'll have an inaccurate position. And if you're trying to land a plane in the fog and you're relying on GPS, you can't get it wrong or you will crash the plane. Okay, so that's very serious. But that's special relativity. It has to do with relative velocity in 2 different frames of reference. It's time lag, but it's simpler. Now, well, not simpler, it's different. But general relativity has to do with gravity. Obviously, it is actually a formula for gravity, which is a spherical phenomenon. And the frame of reference is the center of gravity. Well, you may have more than one gravitational body that you need to correlate to get the true geometry of space, which is how we're getting space into this. You need space-time. Well, that's what Albert invented, space-time. Not really invented. Minkowski actually got the right geometry, but Albert got the right mathematics. Oh boy, that's what makes it work. That's what enables deep space flight. So you need both conversions, but the conversion, for instance, for the GPS system, for the general relativistic conversion, is also nanoseconds. You have to know which way, right? Plus or minus, to adjust your clocks, and which one. It can be quite an interesting exercise in visualization of what you're doing. Well, in the case of general relativity, what you're doing is compensating for the difference between the surface of the Earth, where you're trying to get the position, and the satellites, which are further away from the center of gravity. Since they're further away from the center of gravity, you have to make an adjustment for that based on gravity, not velocity. Okay, so that is a broad introduction to spacetime. Now, what we want is a definition of time. Albert did not actually get a definition of time. What he did, though, was he composed a geometric relationship between space and time, which is quite interesting. Very difficult to master. To make it simple, it is actually quite simple when it's stated the right way. Since there is a time lag in EM transmission, as EM propagates through space, it takes time to propagate. It's as simple as that, but then what do you do to put them together? You try to find a relationship between the spatial separation. Turn this off for a second. Try to get a relationship between spatial separation as it's increasing. There's obviously an increase in the time lag, which also has a metric that's related to the spatial separation. Now, the units are much different, as you know. Over the space of a light year, which is quite a few millions of miles, or meters, a light year is a distance. But you notice the word year is in there. That is the time lag. For that distance, which is an astronomical distance, a light year is, as you know, it's about 4 light years to the Alpha system. The nearest star to us is about 4 light years away. It's a distance. It's also a time. It's 4 years for light traveling at its natural speed. So that is a linear relationship. quite amazing that it's linear. It enables us to compute distances to stars because the linear spatial separation is linearly correlated with the event separation. And that's a technical term which you should learn. Event separation. It's not a separation of space. It's a separation in a time frame. Well, that's what Einstein figured out was a space-time frame. Not just a spatial frame, which is 3D, but he worked in a time frame using a fourth axis, which of course would have to be imaginary. And that works. He made it work. It'll take you years of study to try to figure that out, unless you did what I do, and you're motivated enough, and I had very little background in mathematics, but I was able to learn about general relativity and space-time and gravitational space computation. These are all synonymous. Space-time and relativity are very closely related. But what we usually say, or I will say, to keep it at one term, just give it one term, it's space-time, which is a geometry. Now, I do geometry here, so of course I had to learn this, which I've tried several times over the decades to learn space-time mathematics, and I gave up each time because I'm not very good at mathematics, sorry, but I'm not. But you don't have to be. What you have to be good at is geometry. So if you do want to learn the Einstein field equation from the inside out, all the calculus, all the nitty-gritty details, I strongly recommend DrPhysicsA. That's a YouTube channel. Doctor, I think it's just DR, space physics, or it's actually one word, DR Physics, DrPhysicsA. I'll remember to put this into the notes. In fact, I'm going to write that down. Put DrPhysicsA. All right. So I'll have that in the description so you can, if you're interested. I saw his video presentation twice. I believe it's 4 hours long. So, I mean, you're looking at some time. I listened to the whole thing. It's extremely well presented. DrPhysicsA, much better than Dr. Leonard Susskind. Much better. Although they're different, and that's not quite fair to Dr. Susskind. But DrPhysicsA, I watched that once, and I thought I had it. I really felt good. But then, you test yourself, right? You see if you understand it, and I wasn't convinced I understood it. So I watched it a second time. And it's a very, very good thing I did. And I probably could stand to look at that a third time, but DrPhysicsA, which will be in the description, I won't forget, will give you what you need if you're interested. And you might be. I strongly recommend it. If you're even unsure, I'd like to encourage you to look at that, because even though it's incredibly intricate, at least you'll know something about its intricacy, so it's not a complete mystery. Ultimately, it can be understood. I understood it, and if I can understand it, anybody can, okay? So where we're at now is simply we are covering time-space, and that's enough for that. This is to introduce a full series, which will be running through September, on all 8 of these topics. So you're getting an overview now of what's to come. And I have to do this now. I mean, it's not like I'm resisting, but it's time to do this. For your sake and mine, and for science, because of the major discovery that was just made here recently. One of many, actually, but this is this is the one that'll get my foot in the door. The next item down you'll see is the universe. And of course, that's a major topic these days. We'll just highlight that there. There's the universe. And when you talk about the universe, the first thing that you have to deal with if you're trying to conceptualize it or do anything with it, it's infinite. It's spatially infinite. It's of infinite extent. Now, of course, the physicists are trying to figure that out, because if they could, that would be a major inroad, a major step. That has not been done. Infinity has not been rationalized ever. I've rationalized infinity the only way I believe it can be rationalized. But it definitely works, and we're getting to that. So the universe in infinity, which, just to catch up here on our little bulletin board, there is the second topic out of 8. The third one is the quantum. Now, the reason I chose this image is because it shows superposition in a way that's kind of visually interpretable. Let me help you interpret this, because I'm helping you because the physicists themselves need help. They don't understand this, so don't be daunted by this. But it is important to understand at least what is the problem. Why is quantum mechanics so baffling to the physicists? All right. It's because of superposition. Now here you see that I have a diagram, a little image here, that shows superposition as a sphere. That's actually very important. That's a very good image. But what is superposition? Now, you've surely heard of entanglement. If you don't understand it, you're certainly not alone. John S. Bell wrote books about this phenomenon, entanglement, and actually came up with a formula, the famous Bell inequality, to do essentially what Dirac did and just give some kind of tools to even talk about what is entanglement. I've given several presentations on this, including, I believe, a very good one recently, but to sum it up, entanglement is when you take two electrons. This is an electron phenomenon, although there's a huge footnote, as you can guess. It doesn't necessarily only pertain to electrons, and in fact, it also pertains to photons, and I'll get to that in a moment. That's not as fully understood, but I understand it. So I'm coming out with a lot of statements here of stuff that I understand that physics doesn't understand. That's the nature of this geometry that I discovered. Okay, so look at the second image, two smaller spheres that have the caption entanglement. What is entanglement? You take two electrons and you put them into proximity. This is strongly abbreviated because there's actually several methods that are used to create entanglement. I'll leave it at that because this is the cutting edge of pragmatic physics. What is actually being studied right now as we speak, physicists are trying to figure this out. You have two electrons that you coordinate essentially with a magnetic field. This again is extremely abbreviated, but now they're coordinated. They have a known coordination state. That is, their individual states are now not randomized, where either one could be in any state. Now they're coordinated, but it's only on one aspect of the state, and that's called a polarization in one context. You could think of it that way. It's quite accurate, or it's accurate enough. Remember, this is very difficult to even talk about. It's a paradox. I want you to see the paradox so you know what the problem is. Entanglement shows it beautifully, but what we want is to understand superposition. They're strongly related, and I discovered that fact. That is a provable relationship between the two, you could say, phenomena. Well, entanglement is quite magnificently baffling, and here's why. Once you have the two particles coordinated, I'm just going to do that to show they're coordinated, now you separate them spatially. Well, from our immediately prior discussion, you know that as they're being separated spatially, there is a linearly coordinated event separation. Now, there are two different data types. One is event, and the other is space. Those are not the same. One is temporal. The equivalent term for spatial is temporal for time. So the spatial separation, according to relativity, implies an event separation. Now, what's been done, and this is virtually incredible that these kind of measurements can be done. It's taken decades to make the measurement that is needed for Bell's inequality testing. So to make this totally simple, when the two coordinated particles are separated, they remain coordinated, and now when you measure one, the other one changes. The question is, does the coordinated particle that's not measured change without an event lapse, with no time, in other words, simultaneous? Well, that would seem to violate special relativity. I will be showing you that it actually does not violate relativity. What it does, it redefines relativity geometrically. This is an insight that physics does not yet have. That's from Anagalactic. So that's where we're going with this, so we can get a definition of time. We do need to understand much more accurately now what is time. What Albert discovered is that time is orthogonal to linear space. It's orthogonal to 3D space. And I think you see the problem. Is space actually 3D? No. No, that's a grid. That's a grid overlay on space. Space is not linear. Space does not have a linear characteristic. But we've convinced ourselves that it does, because in order to get a distance measurement, it by definition is on a straight line. That's confused us. It's confused our mathematicians. It's confused our physicists, because their linear system, which is based on a grid, no longer corresponds accurately enough with reality. Reality is not 3D space. So Albert simply accepted 3D space for what it is, a 3D linear system. And he added another line. How did he do that? Is there really a linear relationship between space and time? Yes. I just showed it to you. It's called relativity. A spatial separation has an equivalent, a linearly equivalent event separation. So what's their relationship? Albert showed that they're orthogonal. That is, you can think of them as being orthogonal. Well, the only way you could think of space and time being orthogonal is if they actually are orthogonal. But what I discovered is there certainly is an orthogonality. We know that now from Albert. He proved it. Time is perpendicular. You must not say space. It's not linear. First of all, time, we're not sure if it's linear, but we can certainly think of it as linear. It appears to be constant in frequency. That is, time moves as an arrow, but it's not changing velocity. Now, at grand scale, that's been questioned too, but for just ordinary life, time is linear. You should say it's apparently linear. It's also unidirectional. It doesn't go backwards. It only goes in one direction. That has to do with motion, and that's the key. What is perpendicular is linearized time with linearized space. And I've proved why that's true. Superposition. This is the key to the quantum phenomenon for a layman, such as you or myself. What is the quantum? Well, let's look at that diagram one more time. We have superposition over on the far left. That's just one thing. It's not two coordinated electrons with a purely spatial separation with no event separation. That's what it amounts to. That's what entanglement is. It's spatial separation without relativity. They think that they're the same thing in time, because it's now been shown almost certainly conclusively. It's a very difficult measurement, as you can imagine, because you have to measure one particle and then figure out if this one changed at the same time. Well, that's really difficult. But it has been shown, almost certainly, I believe it has been shown. Actually, I know that this has been shown, because it conforms exactly with what I know about the geometry of what's happening. The two coordinated particles are in the same event state, which is a different dimension. Oh, that's where it starts to get spooky. It's a non-spatial correlation. Well, that's in a different dimension. So that's entanglement. Now, what is superposition, and why does this diagram imply that it's different? Because it's showing just one thing. It can be thought of as the inverse of coordination, and it is a form of coordination. But it does, again, get spooky, because superposition means that it's in two states at the same time, where the two states, it cannot be in both states. So it's somehow in both states. And the way that's formulated, for the sake of commoners such as ourselves, the best way to face that strange fact that one particle can, it's not a particle, it's a system state, the state of a system, can have one of two outcomes. For instance, if a cat is asleep or awake. I don't like alive or dead, but the reason Schrödinger came up with his cat paradox was to show the infamously baffling nature of quantum mechanics, so that you would be afraid of it. He was. Everyone is, who has an ounce of sense, because it violates natural mechanics. Because the two possible outcomes can be proved by a certain trick to exist at the same time. I've proved that it's not at the same time. And that's a strong relationship to the illusion of entanglement. It is an illusion. Well, superposition is also an illusion. So all of this stuff about a split universe, this comes from the Schrödinger's cat paradox. That to face that and somehow rationalize it, you say that there are two universes. Well, that's psychotic. But superposition itself is the opposite of psychotic. It's reality. So that's what we're trying to get at. So that's our third topic. Our fourth topic is the atom. And to save time, I'm not going to go into great detail, but this will be a long lecture. We're coming up on an hour. I'll cut this off at an hour, as I promised before, but we do want to wrap up on the atom. The atom, of course, is well known, although it has come under increasing scrutiny, because the atom does exhibit or invest itself with the same strange qualities of quantum mechanics, of course, because the atom is made of two particles. The proton, which also has a neutron state, but you can disregard that. The neutron and the proton are the same particle with a different characteristic. So they are quite distinct. They're quite distinct, but they transform into each other. So they are the same particle. So the atom is made of the proton, and what's the other one? The electron. And the critical insight that you would need just to have a firm grip on the construction of the atom, no matter what anyone says about bell-shaped configurations, no. Those are mathematical overlays of a purely spherical system. Well, the proton is purely spherical, and it generates a spherical force field. The electron does not have a center, and therefore is not at all the same as a proton. The proton has a definite center, and it's actually the only center we've found in the universe at all. And that wraps up our discussion. We're coming up on 1 hour. Stay tuned. We'll be right back today. I'll have another lecture, and thank you so much for your attention. It means a lot to me. It means a lot to science. We're all in this together. This is collaborative, communicative, and consensual. No one's trying to one-up anyone else or pull the pillars down on your money pipeline. Everything that I've discovered enhances science. It doesn't replace anything, but it will be felt to be a threat. And that's just sad. It's the way of governments, and science is now a full-fledged government, which means we're all dead. Not here, Daddy-O. We'll be right back. This is Anagalactic, bringing you the secrets of the universe. Keep looking up. We'll be back later today.